The second derivative test. Welcome, everyone. Let's begin our lesson on the second derivative test. To start, let's look back at what we have already covered. In the previous section, we learned about the first derivative test. As you recall, that method requires us to examine the sign of f' of x on both the left and right sides of a critical point to determine the behavior of the function. While this approach is certainly effective and reliable, it can be quite time-consuming, especially when dealing with complex functions or multiple critical points. This is why we introduce the second derivative test. It provides us with a more direct and efficient method to achieve the same goal. Essentially, this test allows us to determine whether a critical point is a local maximum or a local minimum, without having to check intervals on either side. However, please keep in mind that this method is only applicable provided the function is twice differentiable at that specific point. In the upcoming slides, we will explore the concept of concavity to understand exactly why this test works and how to apply it step by step. Understanding the concept. Now that we have introduced the second derivative test as a more efficient alternative to the first derivative test, let us dive into the underlying logic. This test relies entirely on a concept known as concavity. To understand this, consider the first scenario. If the second derivative of f of x is positive, the graph is described as being concave up. A helpful way to visualize this is to think of the shape of a cup. Because the curve is opening upwards, any critical point located at the bottom of that cup must be a local minimum. Conversely, if the second derivative of f of x is negative, the graph is concave down, which is shaped like a cap or an inverted bowl. In this instance, since the curve is opening downwards, the critical point situated at the very top of the curve is a local maximum. Understanding this relationship between the sign of the second derivative and the shape of the graph is crucial, as it leads us directly into the formal working rules we will discuss in the next slide. The working rule. Now that we have a conceptual understanding of concavity from the previous slide, let us look at the formal working rule for the second derivative test. Suppose we have a function f of x that is twice differentiable at a specific point x equals c, and we have already established that c is a critical point where the first derivative, f' of c, equals 0. Under these conditions, we can determine the nature of the point c as follows. First, if the second derivative, f' of c, is less than 0, the function is concave down, which means the function has a local maximum value at x equals c. On the other hand, if the second derivative, f' of c, is greater than 0, the function is concave up, indicating that the function has a local minimum value at x equals c. However, there is a possibility that the test fails. If the second derivative, f' of c, equals 0, the second derivative test is inconclusive. In such a case, the point x equals c could be a local maximum, a local minimum, or a point of inflection. Because the second derivative does not give us a definitive answer here, you must revert to the first derivative test, which we touched upon at the start of this lesson, to determine the nature of the point. Once you are comfortable with these rules, we will move on to the step-by-step procedure to apply this in practice. Step-by-step procedure to find extrema. Now that we have established the theoretical foundation of concavity and the general rules, let us organize this into a clear, step-by-step procedure for finding local maxima and minima. First, in step 1, we begin by finding the first derivative of the function, which we represent as f' of x. Once we have the first derivative, we move to step 2. Here, we set f' of x equal to 0 and solve for x. This process allows us to identify the critical points of the function, which we can label as c1, c2, and so on. Next, in step 3, we find the second derivative of the function, denoted as f' of x. For step 4, we take each of the critical points we identified in the second step and substitute them into the second derivative, f double prime of x. Finally, in step 5, we apply the rules we discussed previously to determine the nature of these points. If f double prime of c is greater than 0, the function is concave up, and we have a local minimum. If f double prime of c is less than 0, the function is concave down, and we have a local maximum. However, if f double prime of c equals 0, the second derivative test fails to provide a conclusion, and we must revert to the first derivative test to analyze the point. In the next slide, we will apply this exact sequence of steps to a real-world example involving production costs to see how this works in practice. Real-world example: minimizing production cost. Now that we have discussed the theoretical rules and the step-by-step procedure, let us apply them to a real-world scenario to see how the second derivative test works in practice. Please look at the problem on the slide. A company has determined that the cost, represented by C in thousands of dollars, for producing X units of a product is given by the function C of X equals 2x cubed minus 15x squared plus 36x plus 10. Our goal is to find the production level, X, that minimizes this cost. To solve this, we will follow the exact procedure we just outlined in the previous slide. Starting with step 1, we need to find the first derivative of the cost function, which we call c prime of x. By applying the power rule to each term, we get c prime of x equals 6x squared minus 30x plus 36. Step 2 is to find the critical points. As we learned, the second derivative test is only applicable where the slope is 0. So, we set c prime of x equal to 0. This gives us the equation, 6x squared minus 30x plus 36 equals 0. To simplify this, we can divide the entire equation by 6, which leaves us with x squared minus 5x plus 6 equals 0. Factoring this quadratic expression, we get x minus 2 times x minus 3 equals 0. Therefore, our critical points are x equals 2 and x equals 3. Now we move to step 3. Finding the second derivative, known as c double prime of x, we differentiate our first derivative, 6x squared minus 30x plus 36, which results in c double prime of x equals 12x minus 30. Step 4 is where we actually perform the test to determine the nature of our critical points. We substitute our critical points into the second derivative. First, let us test x equals 2. Substituting 2 into the equation, we get 12 times 2 minus 30, which is 24 minus 30, resulting in negative 6. Since c double prime of 2 is less than 0, the graph is concave down at this point, meaning x equals 2 is a local maximum. Next, let us test x equals 3. Substituting 3 into the equation, we get 12 times 3 minus 30, which is 36 minus 30, resulting in positive 6. Since c double prime of 3 is greater than 0, the graph is concave up, which confirms that x equals 3 is a local minimum. In conclusion, to minimize the production cost, the company should produce 3 units of the product. As we move forward, keep in mind how critical it was to first find the points where the first derivative was 0 before applying the second derivative. We will discuss some common pitfalls regarding this in the next slide. Common mistakes to avoid. Now that we have walked through a practical example, let us discuss some common pitfalls to ensure you apply this method correctly. First, be careful not to ignore the first condition. A frequent mistake is calculating the second derivative of f at c without first ensuring that the first derivative of f at c equals 0. It is crucial to remember that this test is only applicable at critical points where the slope of the function is 0. Second, let's address sign confusion. It is a common error to assume that a positive result, where the second derivative of f at c is greater than 0, indicates a maximum. This is actually the opposite. As we mentioned when discussing concavity, a positive second derivative means the graph is concave up, shaped like a cup, which means the critical point at the bottom is a local minimum. Finally, do not assume that if the second derivative of f at c equals 0, the point is automatically a point of inflection. In such a case, the second derivative test is simply inconclusive. It does not provide a definitive answer. To determine the nature of the point when this happens, you must revert to the first derivative test that we discussed at the start of this lesson. Keep these points in mind as we move to our final summary. Key takeaways. To wrap things up, let's summarize the key takeaways from this lesson. As we discussed at the beginning, the second derivative test serves as a faster and more direct alternative to the first derivative test, provided that the function is twice differentiable. First, if the first derivative of f at c equals 0 and the second derivative of f at c is greater than 0, then the function has a local minimum. Just remember our discussion on concavity. A positive second derivative means the graph is concave up, like a cup, which places our critical point at the bottom. Conversely, if the first derivative of f at c equals 0 and the second derivative of f at c is less than 0, then the function has a local maximum. This is because a negative second derivative indicates the graph is concave down, like a cap, placing our critical point at the very top. Finally, if the first derivative of f at c equals 0 and the second derivative of f at c also equals 0, the test is inconclusive. As we highlighted in the common mistakes section, this does not automatically mean you have a point of inflection. It simply means the second derivative test cannot provide an answer, and you must revert to the first derivative test to determine the nature of the point.